All right, so let's get started, guys. Welcome. It's Friday. Guys on the Zoom, let me know over, like, just talk to me. You're in my ear, so just let me know that you can hear me and that you can see the slides.
Yeah, we could hear you. And
Yeah,
see it.
we can hear and see.
Awesome. You guys are here. Thank you so much. All right, so let's get started. Like I mentioned, homework 1 is out. We have changed the due date 2 days past. So instead of being due on Sunday, it's going to be due Tuesday. This does not, like every other homework has been pushed back as well. So it's not like I'm asking you to do extra work or anything like that. Mostly due for the snow days. All right. Homework 0 has been graded. So you should have received an email from Gradescope. I believe Chi, who's our TA, also put it on Blackboard. So you probably got an email there. If there's any issues with the grade, reach out to us. But the vast majority of you basically got a perfect score. So there probably aren't any issues. But if you have any questions, like, definitely reach out. All right, so in this lecture, we are going to continue where we left off last lecture. And we are also going to learn about recurrence relations. All right. Hey, guys. All right. So again, a couple of other reminders, like I mentioned, I do have student hours today from 1:30 to 2:30. Yeah, question? Yes. I have adjusted the slide, so we're going to finish going over merge sort. We're actually going to finish coding it right now. So I do have student hours. That's a reminder. Also, a couple of notes. The course website is not accessible from the school Wi-Fi. So I was mentioning there's an alternative URL here. I've also been told by Maya that you can access it if you're on the VPN. So again, I am trying to get that resolved. Hopefully it's fixed by next week, but it is currently outside of our control. So all we can do is kind of have workarounds for it. All right. She is also she updated the course website. She has Zoom links now to when she's doing. So my Zoom is this link, and then her Zoom is there for when she does student hours as well. Those just reminders. Cool. So yeah, picking up from last time, we were doing a live coding. So I'm going to bring that up again and try to zoom in a little bit more. Again, let's actually just start from the beginning so you guys can. So I'm going to delete this code. Yeah. It is being recorded currently. Yes. Thank you. Thank you for reminding me. It is being recorded. Yeah. So it will be online as well. But yeah, I just want to wrap up from last lecture. And let me zoom in a little bit. Hopefully this is easier for you guys to see. But yeah, if you guys want to keep up the slides open for the pseudocode for merge sort. So we did this last lecture, but let's do it again. So what's the first thing we want to do when we're writing merge sort in code? Yeah, back there. What's that? Split up the vector. So there is going to be a part where we're going to need to like split up the vector into the left and right sides. Sure. So we can do that. We could say, const standard vector int, let's say left half equals. Do you guys remember how we split up the vector last time? How we made it was in one line of code. We didn't have to do that much, but yeah. So input, why are we using input? We're using input because that's the name of our vector here, right? Let me close this out. Is this big enough for people to see, or should I zoom in a little more? A little bigger? How is that? I think I can close this too. Let me zoom in a little more. All right, so we're here. All right, so somebody mentioned input.begin, comma, input.begin plus, what's after this? N divided by 2, right? So that means we need an N, right? Sorry, it keeps like freezing up. Okay, anyway. So we define an N, which is going to be equal to input.size. Does that seem fair? Right? And then we do N divided by 2 here. As you mentioned in the back, we also want to split up the right half. So here we do, yeah, how would we do the right half? Yeah, input.begin plus n divided by 2. And then we go all the way to input.end, which is the end. And somebody asked a really good question. Do we need the +1, -1? And if you guys remember, I talked about how with this syntax, it's not creating a vector with just 2 elements because we're giving it iterators. So it's actually creating the vector from this element all the way to this element, but not including it. Yeah. Yeah, you could write it. You could write merge sort. So right now, what this is doing is it's just splitting into left and right, right? We have not merged it yet, but that is a good question. So, somebody mentioned in class, so the next thing we want to do is we actually want to sort the left and right sides, right? So how do we do that? We say, okay, let's just make a new vector. Why not? Of integers, and we're gonna say, oh my God, can't type. Sorted left equals, how would we sort the left side? So here we have 1, 2, 3, 4, 5, 6, let's say that's our input. So here we split it into, let's say, okay, this is already sorted. So it's kind of like, okay, let's say 1, 3, 2, 6, 5, 4, right? So when we split it, the left half is going to have 1, 3, 2 in it, right? And the right half is going to have 6, 5, 4. So according to our pseudocode, how do we sort these 2 sides? Because now we want to sort them. We actually want to sort them. So that's merging if we want. So they're not sorted yet, right? We just split it up. So in the solution, I do both things in one line, but here we actually split it out. We said first we're going to split them. So they're just split, but they're not sorted yet. So this is where back there. Yeah, I think you mentioned, you just call yourself. So this is where you do like, oh, magic, I'm not going to worry about it. I'm going to call myself. So you call merge sort on the left half, and to sort the right side, you're going to call merge sort on the right side, right half here. Okay. So now here, after these lines run, we expect the sorted left to be 1, 2, 3. We expect sorted right to be 4, 5, 6, right? Because So, great catch. Did you guys notice that? He said we need a base case. So you guys kind of jumped into the inductive step, but you do need a base case. So where do we put our base case, and what is our base case? Got it. So here's the base case. So we need a base case for recursion, right? And in this case, we're going to say like, okay, if n is less than or equal to 1. So if either my array is empty or it's just one of them, that is the easiest solution. This is our base. In the inductive proof for this would also be your base case, right? It's like in the easiest case, what does it look like? So what is the answer in the easiest case? Right. You just return the input. Whatever your input is, you just return that. Okay. So we do have a base case. We split it into left and right. We sorted the left and right sides. And now we get to the hard part, which is actually you have to merge them. So I know already that merge is actually a lot of code. So what I'm going to do is I wrote another function to do it. So here I'm just going to write return merge, sorted left, sorted right. Because I don't want to think about it right now. So here it's like I'm done. If merge existed, if merging 2 sorted arrays, if I had that code, I'd be done, right? Does that make sense to everybody? All right, but now let's go and write merge. So that I know ahead of time this is a lot of code. That's why I didn't write it in the other part. If you were writing it for the first time, you might not know. So you would start writing the code and you'd be like, damn, this is a lot of code. So then you might write a function, all right? So now we have, left and right. This is a separate function. You can forget everything about merge sort because now we're just thinking about this function. And all it does is it's going to take 2 sorted arrays, already sorted, and it's going to merge them into a new array. Cool. So how do we do that? right, so somebody mentioned setting up the indexes. So we would do, like, let's say int I equals 0. Const, actually, these are not consts. Forget that. It's going to complain because I'm going to change them later. Int j equals 0. So these are like our 2 pointers. If you remember from our slides, if you're looking at the slides, that kind of walks you through it. That we have that example. We're like pointing at the, let's pretend we're doing that, right? So what's our example? So left is going to be, 1, 2, 3. Right is going to be 4, 5, 6. So this is a bad example because the way you merge them, they just all end up to like you pull from the left all the time and then from the right. But you can imagine it might be like a little like, it could be like 1, 5. Let's say that 1, 5, 6 and 2, 3, 4. Right. So they're both sorted. So they satisfy. We said we sorted both sides, but now we're having to merge them. So we started with I and j, which intuitively we're going to be used them to point into both the left and the right. So we can name maybe this is like left index and this is right index, right? Just to like make our lives a little easier. All right, so what do I do next? Start comparing. Somebody mentioned comparing. Okay, so I know I'm going to be doing some comparing, right? So I want to compare something. All right. What do I compare? The arrays, right? So I compare the elements. So I would say left index, and I'm probably going to compare it to the right index. Okay. So there's all right. So, but then what else am I like? How do I compare? Yeah. Okay, somebody mentioned we need to create a new vector. Okay, so we're on this, like I want to compare, not done yet, but somebody did mention, wait, I need a new vector first. So this is what I mean, like if you guys are working in a group, this is what you can do, right? So it's like, because somebody remembers, wait, I think I need to make a new vector first, right? Somebody else is like, wait, we need to compare. So how do I make a new vector? So I'll just give it to you. So we're just gonna say standard new vector. We're gonna call it sorted. And we're just gonna say it's empty right now because we haven't put anything in it yet, right? All right. So we do have a new vector now, and we are comparing with somebody else finished walking me through this. So how do we compare? Yeah. Yep. Yeah, so it kind of depends on how you want to implement it. So you could create the sorted array so that it's this size right size plus left size. What we're going to do is I'm going to like push back into the vector. So it'll like just add the elements as it goes. Either solution is correct. They are just different. Like, as you guys can see, there's like a lot of ways to write. Like, this is also how we, like, if you guys ever wonder, like, how could people know that like people are cheating or like whatever, it's because like, no matter how simple the algorithm is, there are a lot of ways to like do the same thing. Yeah. All right. So left. All right. But yeah. So great question. Somebody finish me up here. So I'm comparing. What do I compare? How do I compare? Yeah. Sorry, what was that? I want to set up a loop for this. Okay, somebody mentioned maybe there's going to be a loop. Okay. Maybe a loop somewhere. Yeah. Yeah. Perfect. Yeah, that's exactly. So that is the comparison we want to do. So we want to say something like if my left side is smaller than my right side. So this is one time, like somebody did mention a loop. So you should be thinking this is probably going to be in a loop, but just for one step, we're going to say like, okay, if my left is smaller than my right, then what does that mean? So if I'm looking at, so in this case, actually, I'm looking at 1 and 2, and it turns out 1 is smaller. So what do I do in that case? What goes in the if statement? Yeah. Trinity, is that Trinity? Is that you? Yeah, yeah. Right. So I'm going to do this. Perfect. She remembered. And then you increment left index. Because now we put it in and we move to the next one, right? All right. So anytime you have an if statement, you should think, what's my else? Or is there another if I need to check? But what's my else? What if So the else is saying, what if my right side is the one that's smaller? Yeah, exactly. So you can do the same, but for the right side. Right index, and then right index plus plus. All right. And then back there, actually, you've been, what's your name? I keep Leander. Leander? Okay, all right. Sorry if I got it wrong. It's a little, you're a little in the far, but he did also mention a loop. So we're probably thinking we need a loop. You know, what is this a for loop, a while loop, a do while loop? Yeah. Yeah. Yeah, that sounds, yeah. So he said he thinks it's a while loop because with the for loop, you kind of need to know, like each iteration of the for loop, you have one index increasing. Usually you can write it in different, like you can actually write it with a for loop if you wanted to. But the most intuitive thing is like sometimes the left goes up, sometimes the right goes up. So he's saying maybe a while loop is better. So we might write like while, and then, you know, now I have my while loop. I would tab this over to make sure it's inside the while. What goes inside my condition? So you actually kind of spoke it out, but what would I check here? Anyone else want to contribute? Yeah. Somebody that hasn't contributed yet. Come on. How long does this while? So one thing you can look at is what's the code inside my while loop, right? Left index and right index are going to be looking into left and right. So yeah, go ahead. Yeah. So you want to check, you want to make sure that before you run. So one way to think about it is like, if my left index is ever too big, this code that I wrote here is going to crash. And this code is going to crash if my right index is too big. So you're like, let me make sure that's not the case. That's one way to think of like what goes in the while loop. Let's just make sure it doesn't crash, right? So it's not even thinking about the algorithm. It's just like, I just don't want the code I wrote to crash, right? So you would do something you like, let's say left index is less than what? Right, left that size. And my right index is less than right that size. Cool. So that's this while loop. How do you guys feel about this so far? You have a question? So there are a lot of ways to write this. If you did or, then you would have to have more checks inside the loop. So one way that I'm thinking about this, but that you could do or and then have more checks inside the loop, and then you won't do what we're about to do with other loops. So it is possible to do it either way. In this case, the way I was thinking about this loop is while I have elements from both, I know exactly what to do. Like it's pretty easy, like the logic. It's like if I still have elements from both the left and the right, then I compare them, whichever one is smaller, I put into my vector. So I'm like, all right, that's the only thing I want to worry about right now. If you do or, then the logic inside the while loop gets a little bit more complicated because you have to say like, well, it could be that both are smaller, then I know what to do. But if only the right side is still smaller and the left side is bigger, then now like I don't have something on the left to compare to. I just need to take from the right. So you would write that. And that's kind of what we're going to do. Yeah. Somebody have a question? Okay. But yeah, that does bring up to the next part, which is like this while loop alone has basically finished. It'll end when either one is empty, right? Like when I've run out of the left or the right. So I still have elements left over. Is that right? You guys see that? All right, so what do I want to do next? Mhm. Yeah. Got it. Yeah, so again, intuitively, you could write this in comments. Like normally you wouldn't comment this much once you get comfortable with writing code. But you know, I would say like you guys just think about what you're gonna do, like write the comment and then you can see like, okay, I already figured out what I needed to do. I now need to write it in code, right? So she said, you know, if the left one still has elements, then because now we know both of them don't. So it could be either both are empty in case we're done. It could also be that only one still has elements, either the left or the right. So she mentioned, okay, so let's, if the left, if the left index is still, if there's still stuff there, she said, just move it. Because now you've there's nothing to compare it to. They're all bigger than everything else. So now you just move it over, right? All right, this code is right? No, I hear no, yeah. Question? Mm-hmm. When we get back to the slides, I'm going to answer your question because I actually have it all I drew it all out so we can see exactly what's going on. At the very base case, you will have just one, right? You can imagine that after you have merged those two, you go up again a level on the tree, and now you have two vectors that are size 2, hopefully. So that's why you have to write this code generally. So it can't just be like, oh, it's just 1 and 1. So on the base, at the very bottom of the tree, it's 1 and 1. But once you move up again, then it's it'll be 2 and 2, and then 4 and 4. And then the other thing is if it's not a power of 2, you will sometimes get a vector that is 8 and 6, and you have to merge those two. Yeah. Question? Yeah. No. It actually, you're doing and, so that means it only runs when both cases are true. And I'm checking to see if it's smaller. So it'll only run when both sides are smaller than the size. So it actually stops as soon as one of them. So as soon as one of them is bigger, this and is going to be false, because it'll be it'll be true, false. And then because it's an and in between, it'll the whole thing will be false, right? But yes, I was asking does anybody does this code look right to you guys? Am I done with this while loop? You want to increment the left index. If you're really clever, you can actually do it like this. But you could also do this, or you could do this. So again, like I said, there's a lot of ways to do the same thing. They're all right. All right. So we did that, and then you guys mentioned, okay, what I want to do for the right side is basically the same thing, except instead of looking at the left side, I look at the right. Right. So I actually just copied the code and replaced, everywhere I saw left, I replaced it with right. All right. Yeah. Question. You can add that. You could say left index is less than left side, and right index, is bigger than or equal to right that size. That is not wrong. It actually does the same thing. It's just, this is always true. By the time you get to this line of code, this is always true. Because if it wasn't true, we would still be in the previous while loop. Yeah. We are doing the recursion, actually. Yeah. So we are doing a recursion. So the recursion is here. This is the recursion. Oh, but in merging, yeah, when you're merging, yes, it is possible, I think, to write merge as well using recursion, which would make it a little bit simpler. You usually don't see it, but yes, I think anything you can write with a loop, you can write with recursion. That is generally true. Sometimes it's a lot harder to think about it that way, or maybe it's easier for you. So whichever way you think, but if you did do merge with recursion, you'd want to remember your base case, and then all these the only thing the recursion would get rid of is it would get rid of the loops, And then but like this same logic somewhere, this logic with these if statements and doing the comparison, that has to be somewhere. Okay. But am I done? Is this it? Did I finish? All right. I have to return my list, right? So I actually have to return my sorted. Is this finished? What do you guys think? So we wrote merge, sort. So I think it's finished. There's probably some syntax errors that we had. So we can try to run it. And then we'll see if it compiles. Somebody asked on chat, length.array. So length.array is Java. In C++, you use .size. I'm not sure why it's taking so long to compile the program. Okay, yeah, so I don't think this is an issue with our code, but it does say the resources are temporarily unavailable. Oh, there we go. So now it actually ran, and you can see that it printed this array. So if you go to main, so this is code you guys did not write, but essentially what I do is I create this array, which is 27, 17, 2. This is just an example. And then I pass it into our code that you guys wrote, merge sort, and then I print it to see what it is. And after I printed it, it says 2, 3, 3, 4, 4, 17, 27, 52. So there you go. You guys wrote merge sort. That's it. Took 15 minutes, maybe? Yeah. Yeah, this code is on the website. Yeah, question? This is why it's being, sorry. So for this while loop, you're asking? Then the right, oh, on the website, I have the wrong code. Oh, okay, thanks. Good catch. I will try to fix that. This code looks right. But again, I guess you should not trust a single test case. So if I have the wrong code on the website, I'll try to, thank you. Bonus points for you for catching that. I will fix it after lecture. I did try to test it in this test case, and I guess it worked. So again, you should never trust just a single test case, because it sounds like if I was saying left here, that's wrong. Okay, that it should be right, 100%. It might be the case that for our example, the example I ran, it turns out the right side, you never hit this condition. So that's why it worked out. Okay, but yeah, this looks right. Let's jump back to lecture. I will try to fix that on the website. Thank you so much. All right, so you guys coded it up. We have 20 more minutes. We're actually going to walk through what's going on. So maybe hopefully this answers some of the questions that you guys were having as to why do we have to check all of this, etc. So this is a bigger example of what it would look like, right? So what actually happens with merge sort is we first start with this big array, right? Just a big fat array. And if you remember, the very first things that we do is we split it and then call ourselves with those as inputs. So that's split into 2, call yourself. And what are those functions going to do? Well, the very first thing they're going to do is they're going to say, oh, split, call myself, right? So actually, before you even get to the merging, you're doing all the splits because you're using recursion. All the splits are happening before anything even gets merged. Does that make sense to folks? Because the way the computer goes, it literally goes line by line. Actually, what's going to happen is the left side is going to get split. Then this side is going to get split. Then this side is going to get split. So the very first thing you're going to get at the very bottom is just going to be a 6. And then you'll get the 4. And then you'll go split this right side, which will split the left first. And that's because the way we wrote the code, we always split the left first, right? At the end of the day, once all the recursion is done, you're going to have these many functions going on at the same time, right? So what happens next? Then we start merging. So once we've split everything up, we get to the base case, right? Because this final call is going to hit our base case, and it's going to say, oh, 6 is of length 1, just return it. So it's just going to say, now I have, instead of 1 array with 8 elements, now I have 8 arrays with 1 element, right? That's all we did so far. And it's going to start merging them back up. So when you come back up, it's going to say like, oh, okay, I need to merge the 6 and the 4. And when I merge them, they actually become 4, 6, right? When I merge the 3 and an 8, 3, 8, 1, 5, 1, 5, 2, 7, 2, 7, right? So that's when it's like, it's coming back up. So it's kind of finishing its recursion and it's going back, it's doing the return merge in each of the functions that we called, okay? And then it's going to repeat that again, right? So it's going to try to merge the 4, 6 and the 3, 8, right? And that's going to say like, well, 4, 6 and 3, 8 merged is 3, 4, 6, 8, right? And then similarly, it's going to do it for this side until it gets to the very first function call that we made. And at the very end, it's going to say, now let me merge 3, 4, 6, 8 and 1, 2, 5, 7. Does that make sense as to like how the code is actually running? So first it splits everything up all the way your base case is, and then it merges them back up your tree. And that's why when we write the merge, the merge, we can always assume these inputs are already sorted. So it makes it a lot easier to merge it. And you can imagine for this case, it's actually 8, so it splits up perfectly. But you can imagine if you had one more element, the way it would work is you end up with like a straggler over here. And then this is like this side of the tree ends up being like 3 and then like 5 or something. So it's like 1 bigger. So that's why you do have to handle the cases where it doesn't work. But you can always draw it out. You can always draw out these trees. Any questions on like this is how you guys wrote the code and this is how it works, right? You could also do it the other way. You could like figure out how it works first and then write the code. Right? Cool. So remember, there's 2 questions in this class that we try to answer with any algorithm that we write. So first of all, I'll tell you guys, merge sort is a pretty complicated algorithm. The way we've taught it in this class, most of the time, your programming languages will already have implemented a sort method, so you don't have to write it. All right. Now, I have personally written merge sort multiple times, not for a single machine, but for many machines. So you do have to have a good idea of how it works if you want to write it for that case, where you can imagine, here when we were splitting and merging, all of this is just happening on my computer, on my single memory. But what people do for like Google, Meta, et cetera, they will implement this same algorithm, but instead of like, instead of these splits happening on one machine, you'll be like, on one machine, I'm going to pick half and half. And then this array, I'm going to send it to another machine to go do it in parallel. And this array, I'm going to send it to another machine to go do it. Okay. So it's the same algorithm, but you have to write a lot more code because you have to be like, all right, I got to like, which machine do I send it to? Like, how do I send the array? Like, how do they share, et cetera. So these algorithms are very useful. And that's usually where like I've seen like merge sort come up. I've never actually had to write it myself for like a single machine, but because usually like just use the library, it'll be written better than you could write it. Unless I'm asking you for a homework assignment to write it, then you should write it. Right. Cool. So any questions on merge sort? Great. So if I ask you guys to write it for the homework or something similar to it, you'd be like, yep. Good. Cool. All right. So the next question. Yeah. Yeah, we're about to cover that. So that's awesome. Yeah. So the questions you should always ask yourself about any algorithm you write is, does it work and how fast is it? All right. So I actually tried it out. So this bottom line is merge sort, the one we wrote, right? These are the insertion sorts that we had before. So you can see, like, even if you try it out up to like 1,000, merge sort is faster. Even though it's a lot more complicated in code, it does seem to be faster, right? Does it work? You can use a proof by induction to argue that it works. Hopefully you guys can kind of like, you are convinced that it works. I wrote it up on the lecture notes if you guys want to look at it. You're not responsible for knowing this proof, but if you want to see how somebody would prove it, it's in the lecture notes. What we are going to cover is how fast it is, all right? So it is actually, the running time is O of n log n. All right. So if you remember anything from this class, you should remember the running time merge sort is n log n. N log n is a lot better than n squared. All right. Does that make sense for people? We talked about this, I think, last time. Now we're going to do a really quick refresher on logs, because I did notice from the diagnostic that only 71% of you got the answer right to what's log base 2 of 32. So there's 30% of the class that maybe was off by 1. Most of you were off by 1, which is fine. That's not a big deal. But all logarithms in this class are going to be log base 2. So you can use other bases, but for computer science, we always use 2 because it's our favorite number. Now, log n is the number such that if you raise 2 to that number, it gives you back n. That's one way to define it. All right. The intuition is that log n is just how many times I need to divide my number by 2 in order to get down to 1. Right. So again, so for this example, what is log of base 32? It's 5, because I have to divide the number 5 times by 2 in order to get down to 1. Right. So I divide once, I get 16. Divide again, I get 8. Divide again, I get 4. Divide again, I get 2. Divide again, I get 1. Right. So the reason I'm refreshing you guys to this is because we are going to be using log a lot. Because a lot of the algorithms we're going to cover are going to be n log n, or like log n. All right. So log comes up a lot in CS. All right. So that's log. What about 64? What is log of 64? It's 6, right? So I just divide one more time. Right. So that's log base 64 is 6. And then the other thing also to keep in mind is that log grows very, very slowly. So it does grow. It goes to infinity. If you do log of infinity, you will get infinity. It's like a huge, it does go to infinity, but very slowly. In particular, the log of the number of particles in the universe is like 280. So if you had an array you wanted to sort that had number of particles in the universe elements, it would only take you 280 times n, right? So log is very, very slow growing. So if you can get an algorithm from n squared to n log n, you've done great work. That's awesome. If you can get an algorithm from n log n to n, it's like okay, but not that great. You know, it's like fine. If you can get an algorithm from n to log n, that's also awesome. All right. Yeah. N log n is much faster. How do we prove? So how do we show that merge sort has this running time? We'll walk through this, but you can imagine. I think we did this with Karatsuba, so you guys should be remembering that we do these trees a lot in this class. A lot of recursion algorithms are going to have these sort of trees. We're going to learn a shortcut next class on how to get the answer without having to do the trees. But you should, the shortcut doesn't always work. It works like 95% of the time. And I want you guys to be like the 5%. I don't want you to be like the 95% that knows the shortcut. I want you to be the really highly paid 5% that can figure out the problems other people can't figure out, right? So if we start here, we can focus on just one of these sub problems. So the question for merge sort is like, what is the running time? And we already know we start with size n, and we create this tree essentially where we like split it up into a bunch of smaller pieces. And then one question we want to ask is like, for each of these pieces, how much time does this algorithm take, right? So if we focus on just one piece, so this is just like an arbitrary piece somewhere. That's why I put n over 2 to the t. It's just like, I'm not saying it's the beginning. I'm not saying it's the bottom. I'm just saying some arbitrary piece in the tree. The time that I spend is the time that I spend merging the two problems, the two sorted arrays, plus the time that I spend with my two subproblems, right? So anywhere in the tree for one node, I spend some time merging my two vectors, and then I call myself, and then I spend some time merging them. So the total time is going to be like, how much time did it take me to call myself, plus how much time did I spend merging the two subproblems, right? And the thing that we're focusing on here is, so how much time does it spend merging? I think I replaced n over 2 to the t with k, just so that we don't have to keep the 2 to the t. It doesn't matter. So how long does it take to merge? What is my big O running time of merging two sorted arrays? Again, you don't even have to look at the code. It's just like, if you think about it in your head, if I have two sorted arrays of length k, or actually of length k divided by 2, because I'm at a problem size k. So I've divided them by 2. I have 2 of them. How many steps would I need to merge them? Yeah. Sorry, what was that? Would it just be k? So I have somebody saying it's O of k. It'll take k steps. Yeah. Somebody else says k squared. Do I want to take a poll in the class? You guys want to raise your hand between those two? Sure. All right. Who thinks it is O of k? Okay, maybe majority. Okay, who thinks it is O of k squared? 1, 2, 3. All right. Who wants to explain to me why it's O of k? Who hasn't spoken up yet and wants to explain to me? Somebody here? One of you? You want to explain why it's O of k? No? Okay, okay, fine. Somebody else that already spoke up. Who? Yeah, go ahead. Yeah, something like that. So he's saying it's 2k half, and you can actually think through it, right? So big O, doesn't matter how you code it. It's essentially saying like, one way to think about it is like, how many times am I looking at my input, right? So each time I look at my input, I look at 3 and 1 once, right? And then I move on from the 1 and I look at the 2, right? So the 1 only ever gets looked at one time. And that one time I look at it, all I do is a comparison, right? So I do like constant amount of work and I only look at it once, right? So similarly for every other number, you can, if you walk through it, wow, my laptop is really like randomly freezing. Okay, if you walk through it, you only ever look at each of these numbers one time. And each time you look at them, you do, or maybe you look at them twice. No, you only ever look at each number once. And each time you do a comparison, maybe an if statement, like some constant amount of work. So the total running time is O of k. We just did this. It takes time O of k. I guess I wanted to ask you guys to talk amongst yourselves, but a good majority of the class. If you still have questions why it's O of k instead of O of k squared, feel free to come to student hours or ask the other students. Right. So going back to our recursion tree. Now we figured out that for one node, we do O of k work. So now the question is, what about at each level? How much work do we do at each level of the tree, right? So on the first level, we do O of n work because there's only one node and we do O of n. Like we have to merge these two lists that are each of sides n divided by 2, right? So the total work is O of n. At this level, for this node, we do O of n divided by 2 work. And for this node, we do O of n divided by 2 work. So our total work is probably O of n, right? Also, the divided by 2 doesn't even matter, so it's O of n, right? Does that make sense? What about the rest of the levels? Well, how much work do we do at this level? Total, how much total work do we do at this level? Yeah, I heard a couple of different people. Somebody want to speak up? Yeah. Yeah, this level, this n divided by 4. Huh? Yeah, so you do n divided by 4 work for one of them, and then you have 4 of them. So in total, you kind of do O of n work. What about this level? The more general, so in general, how much do you think each level work does? Yeah, so for this level, you can see the pattern, I guess. You end up splitting 2 parts, and then you do less work at each part, but then you have twice as many parts. So in total, you actually end up doing O of n work at every level, right? And well, yeah, we can walk through it. So you guys walk me through this. So the number of problems that I have is 1, 2, 4, 2 to the t, right? Because every time I split into 2 more problems. So as I go down the tree, I split into 2 more. Each time the size of the problems gets smaller by a factor of 2. So if you multiply like the total amount of work, it actually is O of n at every single level, right? Does that make sense? Because this is how we get to n log n, all right? So at each level, we do a total amount of work that is linear, even though we split into 2 and each problem gets smaller. So we do less work for each problem. We have more problems, okay? And in this case, it actually balances perfectly out. You can imagine it might not balance. So Karatsuba, we like had 3 problems, but each one was only split in half, right? So we had like 3 problems, but I split in half. So that's probably more than n log n, right? And then you can imagine you have a algorithm that maybe like has only one problem and you split it in half. So that's binary search. You only have one problem that you go to and it gets split in half, right? So the total running time is O of n steps per level at every level. And I have log of n plus 1 levels. The plus 1 doesn't actually matter, but to be correct. So the total running time of merge sort is n log n. How do you guys like, does everybody feel comfortable with this argument and this way of thinking? So if I give you a new algorithm that has trees and has stuff, could you figure out the running time there? Maybe, yeah.
Could you quickly explain why it's log n levels plus 1 again? Sorry.
Yeah. So somebody asked, could I quickly explain why it's log n levels plus 1? Can somebody in the class explain why it's log n levels plus 1? For the very first level. So the way I think about the plus 1 minus 1 is a lot of times I don't actually think through it. I just try out a few cases so I get the right answer. So essentially, I'm saying the size. So if my tree was of size 1, right, I would have 1 level, right? So I say, well, the height of the tree is log n something. Maybe it's off by 1, maybe it's off by 2. What is log of 1? It's actually 0, because how many times do you divide 1 by 2 to get to 1? You don't. It's 0. It's already 1. So if I thought the height of the tree was just log n instead of the plus 1, I would be wrong. And then I would say, like, how off am I? Well, I'm off by 1. So that's why I say, like, if you have a size 1 problem, the height is 1. So you need to do log n plus 1. Does that make sense? Somebody on Zoom asked that. So that's how I think about it. But yes, somebody else also gave the correct answer, which is you have the head. So you need to add a plus 1 to the tree. You can also think about it like, yeah, there's other ways to think about it, but that's one way. Okay, so far we did insertion sort, merge sort. We talked about worst case big O notation, and we analyzed the correctness of recursive algorithms and the running time of recursive algorithms by drawing a tree. Okay, so you guys should feel comfortable with that. The next part, I was going to sneak peek introduce you guys. We are going to learn a shortcut for any recursive algorithm. If you know into how many problems you're splitting it, and you know how small each problem gets, how much smaller. With those two, if you know those two things, there is a shortcut to immediately figure out the running time. Okay, so. But it's essentially a generalization of what we did today with merge sort. So if you understood today, you will understand next lecture. It's just going to add more variables into it instead of one specific example. And then, like I mentioned, the shortcut does not always work, but it works most of the time. And that is, in my job, I most of the time use the shortcut, unless it's some weird algorithm. All right, so that was it. Yeah, next lecture, we'll cover this stuff. And I guess last question, how is the pace? That's good. Did you guys enjoy coding merge sort? It actually takes a lot of time to do live coding, but we can spend more time doing that and less time covering material. I don't know. Yeah. Okay. All right. Anyway, I do have office hours at 1:30. They'll be on Zoom because I cannot let students into Eric building. But yeah, feel free to drop by. And after February 14th, I think the building is going to open, and then we will start doing office hours probably in person as a group. Yeah. All right. See you guys on Zoom. Thanks for coming. Yeah, no worries.